Okay, hi maths gang. Good to be back. I'm going to look at 7D, question 2 and 3, sticking with proof by contradiction. So I'm going to skip contrapositive, I think. But you can do it. But we're a bit short on time, so we're just looking at proof by contradiction. The reason I wanted to do these questions really is to remind you what logs are. You've done them a little bit in year 10, but logs are probably something that's still a bit new to you. You will look at them in year 11. Most schools do in the methods course. Okay? How do I... That line is irritating me. Proof by contradiction, right? Which we covered in the previous video, right? Now in 7D question 2, they give you this statement: 5 to the x equals 12, and they ask you to show that the solution, what's the solution? The x, right? They want you to prove that the x is irrational. Irrational. Okay. There's a worked example on page 217, and it's going to be the same method. There's about 3 questions, exactly 3 questions, and you'll do the same method on all of them. So that's question 2, 3A, and 3B. So let's use that method. I can express this in terms of logs, right? So here's your revision. Logs are a way of getting the power. And we sort of introduced it a lot in year 10, and we started talking about logs, usually in base 10. Right? And he's talked about this would equal 1, right? Or if I had 10 to the power of 1 inside of that. The log of 100, if we're in base 10, equals 2, right? So the log is a function that your calculator can do. It's an algorithm, and it's going to calculate the power for you, right? And that's the purpose of logs, is to show, is when we have powers, to find out what they are. In the old days, logs were also used to speed up multiplication questions if you were doing them by hand, because you can simply add logs, because we've got our log laws, like log of 2 numbers times together is the same as the log of the individual numbers added. Not sure if this will be useful or not. If I had the log raised to some power is the same as this statement. So we're not doing a course on logs, but eventually, hopefully, you'll become fairly familiar with them, right? And they will come up in year 11 again, and they will come up in year 12 methods as well. All right, so we're going to express this as a log statement. And what I mean by that is to say x equals the power, right? So logs are going to find the power, x, right? The base of this power is 5, so the log has to be in base 5. And the log would be of the result, or the answer, which is 12. Right? So this is, I haven't actually really done anything. I've just re-expressed this indices statement as a log statement, right? Now, to prove that x is irrational, we're going to use the method of contradiction, which means that we're going to assume that x is actually rational, the opposite. And if we can show that it cannot be rational, that that's impossible, then we say, well, therefore it must be irrational, because when it comes to real numbers, they've got to be rational or irrational, right? So that's our method of contradiction. To say that x is rational, what does that mean? To be expressed as a ratio or a fraction? I think the book's using p's and q's again, yep. But we've got to be very clear on how we're setting this up. So p and q, they are both integers, right? So they belong to the set of integers, right? We could say this fraction is irreducible, although for this proof it doesn't matter as much. We need to say that the p and the q are not equal to 0. That's probably enough for this proof here. So let's go with that. So I'm going to take this statement here. Sorry about these emails I'm getting popping up. I'll take this and I'm simply going to rewrite x equaling p on q. So log 5 of 12 equals p on q. Now we're going to convert it back to the equivalent statement in an index form. All right, so if our base is 5, logs have given me the power, so this is the power. It's like He-Man, they give you the power, and the answer to the index equation is 12. And this is where the little manipulation, algebraic manipulation, comes in that you will always do for this question. You'll multiply by the denominator in the power. Sorry, not multiply. You will raise this 5 to the p on q to the power of whatever's in the denominator there. So you're going to raise to the power of q on both sides. And then when you're doing this, the way we do it is to multiply the powers, right? So those q's will cancel. You have pq divide q is just p. And so your next line should say 5 to the power of p equals 12 to the power of q. And that is impossible. This is a contradiction. It cannot be. Contradiction, it's out. This is impossible. The reason it's impossible is if p and q are whole numbers, right? So it would be possible to find some value of p and some value of q to make these two statements true, equal to each other, but they couldn't be integers. And we said they're integers because that's what it means to be a rational number. It means you can express it as a fraction made up of whole numbers, expressed as a fraction, right? And if you want to think about powers of 5, right, so what are they? Like 5 to the 1 is 5. 5 squared, 25. Notice how they all have 5 on the end. 625, 3,000 and whatever the next one is. So these powers always terminate in a 5 and they're odd numbers as well. Right? Might go for that line of reasoning. Powers of 12, on the other hand, will be even numbers. And they won't end in 5 either, right? So they'll be even. And therefore, we have a contradiction. We're saying that an odd number equals an even number. That's out. Okay, so if it cannot be rational, it must be irrational. Now let's look at the question 3b. Just erase all this. 3b says, show that log in base 7 of 11 is irrational. Right? So first we say, let this equal x. Right? So we're going to, so that we have an equation that we can actually work with. We're going to say x is rational. Right? So we're assuming the opposite case. I'm going to show how this is impossible. Right? So if x is rational, then x could be expressed as a fraction. Right? We do need to take the time to be very clear on what we mean here. So P and Q need to be integers, belong to the set of integers. They cannot equal 0. And we could add the condition if we liked that this is in its simplest form, that it's irreducible. So the fraction is, how's the book worded? No common factors. Right? No common factors. Why not? Let's whack that in, right? Okay. So, rewrite it. We're going to say log 7. Right, so we're just continuing on from here. Equals P divide Q. That's the same method as the last question, right? So if this is our base, raise it to the power of P on Q because logs are giving you the power. And that would equal the result 11. Then we do key manipulation that we do for these questions is to raise everything to the power of Q so that we can cancel out these Q's and be left with this statement. 7 to the power of P equals 11 to the power of Q. Now this is a contradiction as well, but it's going to take a little bit more thought, and it actually rests on the fact that 7 and 11 are prime numbers, right? So this is a contradiction, right? This cannot be true. Right? We have a contradiction, but you couldn't, like in the last question, I could say, what were the numbers? 5 to the power of P was odd, and 12 to the power of Q was even. Right? But in this instance, these powers will both be odd, so I can't go down that line. What's really key here is that both 7 and 11 are prime, and we can't get underneath that. Right? I want you to focus on the 11 to the Q. Right? So that 11 to the power of Q, 11 is the smallest factor that you can have in that expression. Right? You can't get factors underneath that, like 2 or 3. It's like what we were doing at the factor tree before. Right? We can take some number. Maybe we should make it a squared number. Actually, no, let's do this one. Let's say, well, first, let me just write out the powers of 11 there. 11, 121. I've got to think of Pascal's triangle here. For the next one, 1,331. That's 11 cubed. It's a nice little trick for powers of 11. 11 to the power of 4 is 1, 4, 6, 4, 1. All right. And the smallest factor that any of these numbers have is 11. Okay? All right? Because that's the prime factor. If I give you an example of a different number, 81, right? Just think of its factor tree. Maybe we could do 27 times 3 is 81. And there's a prime factor there. The 27, we could break that up into 9 times 3. The 9 is 3 times 3. And 81 is 3 times 3 times 3 times 3 equals 3 to the power of 4, right? So that there is prime, right? And you don't have any factors in 81 that are smaller than that, right? So when we're considering our 11 to the power of q, there's no way that I could have a 7 inside of that 11 to the power of q expression, right? So because they're both prime, we can say this is a contradiction. You might be tempted to maybe go down some other lines of reasoning, but you know, for example, what I'm thinking of is if I went back to this expression here, I could deduce some certain things about P and Q. They're not going to be helpful, but you know, they might be worth talking about. So when you've got a log in a certain base and the result is greater than that base, then the power would have to be greater than 1, right? So it's like log in base 7 of 7 is 1, right? But we're bigger than 7 here. And so I could start thinking, well, therefore, P on Q has to be greater than 1, and therefore P has to be greater than Q. Right? And that's interesting, but it's not actually going to help us very much, right, in this particular example, because if I look over here, logically P does have to be greater than Q for this expression to be equal. And this expression could be equal if P and Q were not integers, right? But we have defined them as integers at the start. So that is really key to doing the proof. P and Q need to be integers. That's what it means to be a fraction and a rational number, right? Because there could be decimal values that make this statement true, right? And then the other key thing here is that this 11 to the power of q, that 11 is already prime. There are no factors in 11 to the power of q smaller than 11, right? So I cannot say that 7 to any power could exist inside of 11 to the q. Right? So that one's a little bit more confusing possibly, but hopefully this will get you thinking about some interesting ideas in mathematics.